Okay, so yeah, so for my RC3 presentation, I'll be talking about AI forecasting approach for extreme flooding in South Sudan, in particular for predicting out of sample extreme seasonal flooding. So I've been asked to remind everyone that during the session, update your name to your name and your organization name. Um, Mute your microphone. You can keep your video off, they said, but I don't think it really matters unless your own cognitivity is low. Feel free when I'm talking at any point to use the chat to ask questions. I'm also happy if you just unmute yourself and ask a question as well, because I can't see the chat super well while I'm sharing my screen. So I would really encourage any questions or comments throughout. And the session will be recorded. And I think made available afterwards. I've also been asked to say that if you would like captions or translation, you can turn on captions. I think somebody already made a request for that by using this button at the bottom of Zoom. And you can enable translation to non-English languages if you prefer that for comprehension. So yeah, without further ado, so my name's Jess Rapson. I'm a machine learning researcher. I'm an incoming DPhil student at the University of Oxford, and a visiting scientist at the University of Reading. My role is I work on this INFLOW project. That the goal is improved anticipation of floods on the White Nile, and it's sponsored by the Canadian Research Council and Google, among some other donors. Um, so the goals of this presentation, essentially, it's kind of more, I hope, of a more slightly interactive presentation where we can get some comments in discussion from some people in the audience. If not, that's completely fine. It's kind of early in the morning. I'm happy to just ramble as well. But the goal is to kind of understand some of the challenges of predicting extreme events. Particularly with regards to machine learning forecasting, to brainstorm some potential ways that forecasts for extreme events can be used to trigger early action. So those are actions that are done kind of as a preparatory response for extreme events, such as like flooding, drought, heat waves, and identifying strategies for improving trust in machine learning based forecasting, or maybe even talking about whether improving trust in those forecasts is something we should do. So I'll have three discussion prompts during the workshop that are kind of targeted at different levels of knowledge. So any perspective is useful. I think, the presentation is targeted not just at people who have a technical background, but humanitarian workers, managers, analysts, communicators. So it should be kind of at a level where anyone can engage. And I think all the feedback from those perspectives is quite useful to kind of understanding the problem of predicting extreme events. Um, so yeah, so first we'll talk about forecasting extreme events. So what are extreme events? So these are when our target data that we're trying to predict, so this could be something from flooding to rainfalls to heat waves, um, that falls substantially outside normal patterns. So here's kind of a graph of the flood extent in South Sudan, according to the MODIS satellite data, up until the year mid 2018. So you can see here these peaks, those would be classified as extreme events. So this is at points where the flooding was very high. The flood extent covered a significant portion of the country, and is falling outside the normal kind of variation in flood patterns. So those we would call the extreme events, these little peaks right here. But extreme events aren't the only kind of problem when you're doing when you're forecasting. There's also out of sample extreme events. So these are extreme events that not only are extreme, but they also fall beyond the range of data that we currently have available to us. So here's a map or here's a graph of all the flooding extent in South Sudan up until now. And you can see post 2018 or post 2019, there was extreme flooding that was not like beyond the extent that was previously available through the historic record up until 2002. And this posed a huge challenge for models that were trying to predict flooding in the area because they simply were not prepared to forecast kind of beyond this normal extent. So beyond what was a normal extreme event, we now have these out of sample extreme events that are beyond what models have ever been exposed to or beyond what analysts have been exposed to. So they're very, very difficult to predict. And it's very, very difficult to validate models to know that they would be able to predict something like this because I know, imagine we're just in 2018, we would not have the data available to test whether our model could predict these out of sample extreme events. So these are very difficult for models to predict, and particularly for machine learning models to predict as well because they're very data driven. And they're kind of biased to predicting within what the training data that's available has. So if we're just in 2018, it's really hard to build a model that we can be confident can predict these. So this is a challenge not just in flooding, but in many areas of forecasting for extreme events. That is something that we want to kind of delve into a bit today. Um, so specifically for the context of South Sudan, the Sud wetland in South Sudan experienced catastrophic flooding in June of 2019 beyond any extent that had been previously recorded in historical records, as I showed in the previous slide. So traditional flooding models kind of struggled to predict this out of sample flooding. So those are the physical models that would be using elevation patterns and flow from the White Nile to physically model the flooding. So this is the extent before 2019. The color here is the average amount of time that each 1 kilometer by 1 kilometer area in South Sudan was inundated. So it's roughly following the White Nile kind of area, but it's a bit of a kind of swampy marshland. So this area is also a portion of the time is also flooded. This is the flooding after 2019. So you can see the average amount of time that areas around the White Nile were flooded is much higher. So this is way wetter. And all of these red areas here are new flooding that was not ever flooded, at least according to any of the historic data we have back for the past 23 years. So this is like brand new flooding that we have no data records of. So this posed a huge challenge. So some models that were trying to model the flooding, they were using like the average amount of time that each area was flooded, and then they were predicting the flooding, and then they were filling the map based on how often the cells were flooded. So they were kind of filling like out this pre-2019 map. That map would not be appropriate. It would not be able to predict kind of the post-2019 flooding. So for this kind of prediction challenge, we're maybe expecting the data even in the future to be flooded beyond this extent, beyond what's available to us now. We need a model that's kind of capable of predicting flooding in a way that's not been seen before, and trying to like validate that in a way that we can be more confident that it can predict beyond the data that's available. So yeah, so this is flooding without any historical precedent. So it's very, very challenging to predict that spatially. So I will introduce a prompt. If no one's keen to answer, I can also just ramble and answer away. But essentially, so what are some of the limitations with the ways that extreme out of sample events are currently forecast in your field? So any kind of comments on maybe any kind of forecasting that's done in consideration of extreme out of sample events. From any level of perspective is welcome if anyone has any perspective to share. So I'll just wait a few seconds.
Yeah, I'll I'll try and answer for myself. So I do like river discharge forecasting, so pretty similar. And I guess one of the ways where we try and do it, or at least we try and get some understanding of the uncertainty and potential for extreme, is just by like varying a few of the input parameters of the hydrological conditions or the precipitation events, which is helpful, but it kind of forces you to assume particular types of uncertainty and that we've got the overall physical mechanisms correct.
Yeah, I agree. And I think that's a huge challenge as well, because if you're modeling it, if you can correctly model the physical processes, then you can be way more confident that the future predictions are going to be accurate. So that's a a huge kind of reason why a lot of, if you're using a data-based model, to have it really close to you want to really have a good understanding of the physics of the hydrological
Mhm.
models. So maybe even use kind of like hybrid models, so you have a really good understanding of the processes that are used. So yeah, and make sure that you're using the right variables as well, so it's not just like spurious information. Yeah,
Yeah.
I'm seeing some comments about lack of
Mhm.
historical data or lack of written history. So that's a huge challenge as well. In a way, I think when we did the model for South Sudan, we were very lucky because we had a record going back about 23 years. So there was slightly more data than there were, maybe for other regions. But there are even challenges with that data that we have because it's not necessarily accurate as well. So kind of combining that with things like information from local people who live in the area and getting like their oral perspective on the same event to kind of validate the model, because if they're saying that the flood extent like this, a lot of people were saying, oh, it just comes back every, like 30 years or something like that. We don't have the data for that. So in the minds of a lot of researchers, um, that's just like the data is where it ends, and the data says that. And we don't really have a great method for integrating the fact that people are saying, oh, this comes back every 30 years. Yeah, I don't know, Einar or Gizem, would you want to comment on that further in your specific area?
Yeah, this is Ainur. What I see sometimes is that in places where there are very high rural to urban migration, especially, we lose these stories. I mean, you already mentioned that, in your scientific research, maybe the stories are not perfectly fitting in. But as you also said, that it's important. But sometimes when there is a huge, high level of migration, that is lost also. And people move totally different places and they don't know the history there either. So it's both ways, I think. Thanks.
Yeah, thank you. I think that's a great point. And also super relevant for the South Sudan context as well. Um, Excellent, thank you. There's another comment on a lack of understanding of the geological and hydrological processes for riverine flooding, limiting the forecasting of flood levels and impact on the communities. So yeah, I think from a hydrological perspective, I definitely agree. And I think especially for the context that this model was operating in, it was very like marshy floodlands. So it was very, very difficult to, like, the physical models were basically just failing at predicting it because it's very flat. So normally you're really relying on elevation, you're relying on the soil kind of having specific properties where the water is absorbing. And there's also a lot of vegetation, which really, like, there's no really, like, the vegetation's also very, like, changes over time. So it's very difficult to model that. Charmi, do you have any, do you want to add to that at all?
Hi. Yeah, and another perspective that can be added to this one is also if we want to integrate AI forecasting in anticipatory action, where we are heavily relying on triggers to activate any early action protocol, and with the dynamic or rapidly changing environmental context for riverine flooding, it's really difficult or we're very limited to understanding how to update triggers and how we forecast um um alerts or also other things that we disseminate to the communities. So one feedback we usually get is that the triggers right now are too high. We can't activate our early action protocols. So we can't really, it's really limiting us to forecast anything that we want to do. And we're limited to activating our early action protocols if we want to integrate this to AA.
Yeah, yeah, I think that's a great point. And we're going to circle back to that a little bit later in the workshop, when we talk about like ways to kind of set a trigger for extreme events. So I think that's a great point to raise as well. Thank you. All right, so I think we'll move on. So I'll talk a bit about the model that was designed in the South Sudan context, as kind of like a case study as to how maybe one approach for forecasting these extreme out of sample events could go. So INFLOW-AI is kind of the name of the model that was built to forecast flooding in South Sudan. Oh, got another. So basically it's a two-stage neural network that has dynamic thresholds designed to enhance flood prediction accuracy for extreme out-of-sample flooding with a 2-month lead time. So what I mean by dynamic thresholds, basically there's 2 stages for the model. There is a temporal stage, which just predicts that line that you saw earlier. That was just the flood extent for South Sudan, with a focus on predicting the extreme kind of values of that timeline. And then supported by that is a second stage that predicts the kind of spatial extent at a smaller spatial area. And basically the way this predicts flooding at the spatial area is it takes the values from the temporal stage and it uses that to kind of set a threshold to determine how many cells it's going to fill for flood. But the risk of those cells being flooded is dynamic. So this model is kind of changing over time based on the rainfall and the soil moisture and the kind of local inundation patterns. But the amount of cells that are flooded, so we fill the cells based on, you know, how the level of risk that's predicted for that one. So it's a value between 0 and 1 for how likely the model thinks it's flooded. We fill the number of cells in order of probability of them being flooded based on the temporal model. And this method worked really well because it allowed one model to focus just on predicting kind of the extreme values in a very like simple kind of time series problem. And then it allowed another model to focus on the spatial details. It was very hard to kind of predict the extreme values with just a single stage model, which was just modeling it spatially. So this really allowed us to kind of have the best of both worlds in the same model. So the data sources for this particular model were extensive, I think. So we had flood masks for the region, which we were very fortunate were at a quite high resolution, 1 kilometer by 1 kilometer from the MODIS satellite mission. They went all the way back until 2002, so we had quite a large time series to go off of, which isn't always available for these problems, as was brought up earlier. We have data on the large catchment boundaries for the region. We have live data that's updated about weekly for the height variation in Lake Victoria, Lake Albert, and Lake Geoga, which are the lakes that feed into the White Nile. We have also daily updates to rainfall data coming from the TAMSAT data source. This is satellite data from rainfall that's calculated over East Africa. And likewise for CHIRPS, we have about daily rainfall data for the area. We also have estimates over Lake Victoria because that's the main kind of feeder river. So the rainfall over that area is quite important. We used a large amount of teleconnection indices with the idea that these would maybe expand the lead time a bit. So by maybe being able to detect longer term kind of climate patterns, we could maybe have a better forecast of whether it would be kind of like a particularly wet year, particularly dry year. So that's like the Oceanic Nino Index, the Madden-Julian Oscillation Indices, the Indian Ocean Dipole Index, and the Nino region sea surface temperature. We also had the really detailed basin attributes data from Hydro Atlas, which has really like down to like a very, very small sub-catchment level information on like vegetation, soil attributes, development, like population development density. It's static data, so it's not updated often, but it provides a really good idea as to the different kind of terrain types. And then we have a digital elevation model for the region as well. Not all of these data sources are perfect. Some of them have known issues. Like we know that the elevation models have trouble in the region specifically because there's a lot of vegetation. So often the satellite, when it's calculating the elevation, it's very dense, like kind of like reeds and like grass, that you find in a marshland. Sometimes those are detected as just land. So you get like, it's off by like a meter or more, which can be really like devastating to some physical models. So we're hoping maybe by combining all these sources with like the basin attributes, that maybe the machine learning model will be able to kind of pick up these issues and use kind of historical data to figure out that, okay, these cells are flooded anyway. So maybe it's not just, you know, entirely like we shouldn't maybe overuse the elevation model to predict flooding. So that's the hope. So the one of the techniques that we use to kind of specifically try and target and predict extreme values is what we call seasonal differencing. So basically, machine learning models are notoriously bad at predicting data that falls beyond the range that's available in the training set, as I said earlier. So one way to kind of cheat, I think, or to resolve this is to transform the target data so that effectively no values are extreme out of sample events anymore. So what I mean by this is we seasonally scale the target. So it's just using every value as a seasonal anomaly instead of the raw value. And then you only obviously use the training data to scale this. So you don't have to have any information about the out of sample events in the future. You just scale this using the training data. So just the pre-2018 data in the case of South Sudan. And then we difference the target so that instead of predicting the raw inundation in South Sudan, we're predicting the change in inundation from the previous decade. So from the previous data availability, that's what we're predicting instead. So we're predicting the change from the previous period. So just as an example of what this actually does to the data, so this is the raw target. As I showed earlier, we have all these out of sample extremes, and we're only predicting with this data. We're just using this data to train the model. The model will not see this, and we want to see if we can train on this, how well can we predict in the future? So pretending we're just in 2018, how would this model have predicted the post 2019 flooding? So the raw target, it probably not well. There's a really large number of out of sample extremes there. That's really difficult for a model to learn. When we instead represent the target as this seasonal anomaly, and in our case, the data was available decadally, so every 10 days. So we just scaled it by the historic record. So ignoring this bit, we pretend we don't have access to it. We just scale it using the averages and standard deviation for that decade before 2019. So we scale it, and you can see that kind of changes the data a little bit. We have what we would call like one extreme, you know, event equal to the extreme events that are in the out of sample period. Now we have that in the training set. So that's quite good for the model. And we have way fewer kind of events that are out of sample extreme in this once we scale it by decade. So that's just kind of, you know, taking out the seasonal variability that reduces like a ton of the potential extremeness in the data. And then we can go a step further, and then we difference that seasonal value. And this basically effectively eliminates all of the extreme out of sample events in the data. Now we're trying to predict this, which is the change in flooding compared to the seasonal average, basically. So this is way easier for machine learning models to learn. You can see like basically the data range for the training set and the test set are basically the same. And we have nice examples where the data is going like quite basically to the same range as the test set and the training set. So this is great for the model to learn. So we're basically just tricking the model by changing the data a little bit. We don't need to know anything about the future. This is just information that's available to us from the training set. So from, you know, before 2019 for this data. So we got rid of all those problems. We cheated. So just if you care a bit more about the technical side, so we can just kind of show this is the raw data. So it's standard scaled, so it's not, you know, it's not like raw, but it's the before we seasonal difference it and before we transform it in the way I just described. This is the training set, so the stuff that's available pre-2018, and then this is the test set. So they do not resemble each other at all. The training set is not normally distributed. There's almost no kind of values that are over here, and they're like not like particularly negative. We don't have any values over here that are representative of the test values. Because you see there's a ton of test values that are several standard units higher than the average. So this is not ideal. So this is after standard scaling it. So this is like what you would get if you were transforming your data like as you would for a normal machine learning model. So once we take the seasonally difference target, these distributions look way better. We have the training data. The training data is just normalized. So we now have, the model has a way better kind of understanding of the kind of data distribution that we want to target. So we have like a lot of values around the average, but unlike the previous example, we also do have some values that are extreme, are on the more extreme side of highs and lows. So kind of what you'd want to predict. And then most importantly, the test set now resembles the training distribution. So the test set here is also normally distributed, roughly centered around the mean. And you can see the extreme values in the test in the seasonal or in the training set. They're the same values. We don't have this weird patch that's just not represented in the training set. So this is ideal for the model to kind of better learn the thing that we want to predict, basically. So using this kind of methodology, we were able to kind of decisively beat alternative methods, kind of illustrating the potential for both the seasonal differencing method and then the two-stage kind of dynamic model that I showed earlier. So here's a page of numbers. We tried a bunch of different models in different kind of variations and compared specifically just how the model would predict using the raw targets versus the seasonal difference. And and even whether this could be, you know, like a persistence model, because the persistence model is quite good given that the area is really, really difficult to model. So if we can beat the persistence model significantly, that's like quite good. So as you can see here, yeah, we beat all the models pretty decisively, including for the out of sample values, the out of sample extreme values, which is quite good. You can see on the score here that the model that was chosen using the seasonal differencing like is decisively better than the other configurations that were tested. And we also compared, we did a test to compare whether the seasonal difference versus the raw methods were better like between different models. And we also had a significant relationship between that. So between the same model using the seasonal differencing methodology that I showed in the previous slide, that was significantly better for predicting the out of sample extreme values compared to just using the raw or like the standard scale data that you would use normally. And then this is how the spatial model performed. So we have it comparing to a model that was filling the data based on the historic flow patterns in the region. And we have it compared to a model that was just the persistence fill model. So it's just predicting the flooding 2 months from now being the same as it is now. So the green one is our model. So we were able to significantly beat all of these models in terms of precision and recall and overall accuracy at different kind of thresholds. So this is key because this means that this is I think also precision specifically for flooded tiles as well. So it's much better at predicting floods basically than some of the other alternative models. So that being said, so now we have like a model and we can at the very least say we're more confident that we can predict extreme values than we would with like a standard baseline model. So now how are these actually kind of deployed in practice? Because when you're forecasting extreme events, I think as one of the commenters kind of already said earlier, it's like a slightly different regime than when you're trying to forecast other events. There's like special, like, you know, annual flooding, for example. The extreme events are different and extreme out of sample events are very different. So there's kind of considerations you need to make when you're deploying it. So early action triggers. This is already discussed and I was really happy it was brought up. So basically, for those of you who aren't do anything with early actions, basically they're kind of preparatory responses that are usually done by humanitarian agencies or governments to kind of prepare for kind of weather events or disasters before they happen. And ideally, you would take these before the actual disaster strikes. So in the case of flooding, often that's increasing like the height of the dikes that are surrounding specific communities, or preparing to kind of send like water cleaning equipment to communities, because when the flood hits, usually it's very difficult. It kind of affects like the water supply, so it's very difficult for them to obtain clean water, and maybe even deploying as a preparatory response humanitarian actors who can go and like medical workers, for example, and maybe deal with some communities which might then be isolated because of the flooding and road closures. So these are normally set via a trigger, as was brought up earlier in the discussion. So that's usually like some sort of threshold is passed, and then aid agencies will get together and then decide whether or not to kind of act on that based on the trigger. So it's not just like, checking and making kind of ad hoc decisions as the forecast goes. You have a kind of trigger set in advance to trigger these early actions. As we talked about, so sometimes it's set when a simple threshold is passed, but that's not always appropriate. And I think that's particularly true for extreme out of sample events. So here is the model that was built in the INFLOW-AI model with the standard trigger that was set for the area. So this was just a simple trigger. So they set the trigger back in 2018 when this was kind of first discussed at roughly like 5%. If 5% of South Sudan was inundated, that kind of starts the trigger. So that kind of makes sense in the pre 2019 context, but in the post 2019 context, I don't know. Does anyone want to like just comment what's like obviously wrong with this? The average length of the trigger was, why might humanitarian agencies not want this?
The trigger is also active post-peak for a lot of these events.
Yeah. Yeah, so I think the main issue with this is I think that just the length, like it was the average length is 113 days, which is not a reasonable amount of time to kind of have a state of emergency. So the trigger would be active for all of these. So this would be like not ideal. Not great for the model. So this is just setting it based on the simple threshold. So another trigger was proposed, and this one was set to trigger if there was a change, like a change in inundation between two different measure periods, so between two different dekads, exceeding a specific threshold. So this was tested kind of here. And this one was not ideal either. So you can see, I think it's fairly obvious, this is basically triggering every year. So the return period is 1.3 years. So that's not ideal as well. It's triggering far too frequently. It's not the case that there is an emergency situation every year, even though the flooding does go high. That's not kind of how like communities are responding to it. So neither of these kind of triggers that were written are super ideal for kind of like the extreme events. So as a second prompt, I guess, what might be some ways that like triggers for extreme events could be improved? So what different types of triggers, considering different factors, could be set, or like what's kind of missing from some of the considerations that are used for early action triggers? If anyone has comments, and I will wait.
Hi, Jessica. Can I say a few things like I have in mind? I'm thinking since we are talking about extreme events, and these tend to be much bigger in scale also, I'm assuming. So I was wondering, so two things. One is that I want to hear your advice. Maybe this is not the moment you talk about these things, but you can answer later. What is the advice to communicate these messages? Because it could be so out of their people's memories, one thing. And secondly, since I'm assuming these events will be much more damaging, how do we communicate this with the like government agencies or local governments who are dealing with the infrastructure, like much bigger development issues? So to me, two different communications is needed. And I wonder if you're thinking about these things, may not be in the model, but yeah, I was wondering your thoughts on that. Thanks.
Yeah, no, I think that's excellent. My next slide is on communication challenges. So this is like super relevant question. I think I can comment, I guess, on my specific experiences when we ran this model during the 2024 flood season. We had it deployed live, and we were communicating with kind of operatives who were in South Sudan, and then some of the higher level organizations like UNHCR that were kind of coordinating the response. And we had the UNHCR has gotten like they've run like several feedback sessions, like including kind of government workers and aid agencies and like local leaders in South Sudan who were commenting on how the process worked for them. And I think the overwhelming consensus was that like it was a very top-down kind of approach to to disseminating the information. So basically we would have kind of a technical meeting with like the scientists who are working on the model, and then one person from that meeting would then tell UNHCR, and then they would then tell MSF like what the situation was, and then those people would communicate it to their colleagues, and like that would kind of get disseminated that way. But we were really missing, I think, the local kind of people. Like there was really no dissemination to people who were like living there, and like local community leaders, just because I think like those people have maybe less of an official status. Um, so I think like in the future, it'd be really nice to have some like it's not barring like connectivity issues, having just like a larger group that's present for those meetings and can ask questions. Like even if we have to have like, 100 people in the room or like 200 people, just showing those forecasts to people who actually live in the areas, I think would be really helpful. I think Sarah, do you have a comment?
Yes, yes. Hi, Jessica. This is Sarah from Course. Yeah. Thank you for bringing this question. I think this is really a good question. And actually, I'm not AA expertise, but I just had the opportunity to join our AA project evaluation last year in mainland China. I'm from Hong Kong Red Cross, and we had this collaboration project, and I have this opportunity to observe that how our early action trigger will be effective in our community level. So from this is really very good question. And my quick reflection is that there's never has to be a perfect early action trigger. It's definitely to be, we need to allow the flexibility. And when we set the early action trigger, we do not only consider the local authorities. Of course, we definitely negotiate to discuss with them how to set the best or better early action trigger. But on the other side, I think that we also need to consider our community. So from our debriefing, we do need to we take the effort to visit our beneficiaries and ask them and to bring back their reflection that how do they think that what's extreme weather for them? Maybe the heavy snowstorm. How do they think they are affected by the snowstorm? Maybe for this year they are affected very very heavy, but for next year with the same situation, but they have some more, build their resilience, so better their capacity to deal with the other disasters. So I think this really depends on the local community situations. When we consider the factors, we have more broader minds to discuss with different partner stakeholders to think how can we set the better reaction triggers when we consider the extreme weather. Yeah, this is my quick day. Thank you.
Yeah, no, I think that makes complete sense. And I think that's also like something that is great for communication reasons as well. Like also communicating that, the early action triggers and everything aren't perfect, but by kind of keeping the discussion and having like a point where we can kind of circle back and be aware of when it's time to like pay more attention to the forecast than others. That's like still like it's better than doing nothing. So I think it's better than like any alternative, right? So what we're trying to kind of beat like the alternative, which is no early action or like no forecasts, right? So we're trying to beat that. And yeah, I think I agree. Like definitely having regular discussions with people on the ground to understand how they're affected and how like they in particular want responses to work. Because it's when you're kind of in the forecasting realm, it's also important to remember that it's not just like binary where you have a response or you don't have a response. There's also smaller things that can be done, and even like longer term things that can be done, like developing infrastructure to make communities more resilient overall, so that like emergency responses aren't necessarily needed in the future as well. So I think, yeah, those are all fantastic points. All right, so I'll move on a bit because we're getting close to the end. So the trigger that we eventually went with was one that was, so the goal again to have a trigger that's sensitive to extreme events, and kind of also take into consideration what the community was telling us. So we know that the community, when it's flooded for a long period of time, and it floods, again in the flood season, if the water levels had never fully receded, the community is not really in an emergency state. The issue that we were being told when we were, kind of speaking to people who were working there, including also aid workers who were on the ground from MSF, the issue was when there was a huge difference between the seasonal flood minimum and the seasonal flood maximum. So we built our trigger based on that. So the change from the minimum to the forecasted kind of maximum, if that exceeded a threshold, then we set the trigger to go off for that. So we capture from this like a large portion of the extreme events, and it also is sensitive to the fact that there's not an emergency situation every year. Like if the flooding is high in the previous year, the community is way more prepared to deal with the response, and they don't necessarily need that much help. So this means that we can really prioritize focusing on the events that are actually truly like devastating to the community. So under this definition, we had a way more reasonable 7 triggers that would have occurred in the historic record that lasted an average of 59 days, which is a fairly reasonable amount of time to be in a state of emergency. And also the return period was over 3 years, which is kind of in line with the level of response that was wanted from the Red Cross. So yeah, triggering if this kind of the change in the seasonal extent. So we have, for example, the seasonal minimum here, and then the forecasted seasonal maximum here. So if this exceeded this 5% change, which in this case it definitely did, then the trigger was set. And that would seem to be quite effective in capturing a lot of the events. So just a quick note on communication. So I think this already came up, so this is great to kind of continue the conversation. So as I said, the model was deployed live in the 2024 flood season, and it was automatically downloading data from the internet, producing new forecasts up to 2 months into the future, and it was doing this roughly every 10 days. So we have a retrospective of how the model performed live into the future. So when it was tested for that 2-month period, all the predictions kind of fell within that range, which was fantastic. The range that was forecast by the model. And the flooding roughly followed the pattern. Not exactly, but we were in the right range. And an issue with this as well is that the satellite data is not fully accurate. So sometimes it shows like a decrease in the extent or an increase in the extent that's not necessarily correct. So there's always going to be a bit of uncertainty. So we all kind of, but importantly, the trend kind of was correct, and the prediction at 2 months was also very accurate. So when we were communicating this, it was important to have the right kind of context that were given to practitioners who were on the ground, or humanitarian practitioners on the ground. So this graph this is what I used when I was evaluating the model, but this I don't think is very good to give to anyone because it doesn't really give you the full context for the area. So to kind of provide the historical context all in a single graph, we gave workers, we were supplying this at technical briefings and in communications to humanitarian workers. So this is a forecast that has the flood extent for this year, and it also has the flood extents for all the previous years, kind of colored where the older ones are in blue and the newer ones are in green. And you can see how the current year, where we are forecasting in 2024, we can see how it compares to other years. And we found this was super, super effective for helping people understand how severe the flooding was, because they would look at this is much higher than it's been kind of for most of the historic record, but it's not quite as severe as the 2022 flood event, which was quite devastating. So with that information, you can kind of contextualize it very easily on a single graph versus if you're just showing like this kind of like a single time series, it's not very helpful. So for the final prompt, and any open discussion or questions, I'm happy to take at this stage too. So how can communication challenges for extreme out of sample forecasting be overcome, in general, or for kind of like machine learning or like AI kind of models? And also happy to take any questions at the end as well.
Sorry, Jessica, we have 5 minutes just for you to remember.
Yep.
Okay, this is Ainur again. So, I'll wait if anyone comes because I already spoke too much, but if not.
No, please go ahead.
Okay. I was already thinking about the communication challenges or what can be done in terms of extreme events. And I'm thinking, I'm from Turkey and we have these big earthquake events, right? And not weather related, but in the sense that extreme, and they don't happen every day, but also the impact is huge. So what I observe is that after the event, the public attention is highest. So I wonder if you have thought about after the event, machine learning, like what happens, like what people are paying attention to, and if that can be integrated into the model from the communication perspective.
Yeah, so I think that's a really good point. I don't know if that's actually a solvable one. I think people's attention kind of naturally attenuates after the event kind of passes. But I do think I think like the opportunity there is also to have like as we discussed earlier, like continuing to have the kind of community being able to speak with aid workers and continue to like listen to what they're saying, because again, we're not when we're doing these forecasts, we're not even in the countries. Most of the workers who are involved with the research, just for like safety reasons. But people on the ground were saying like, hey, like this flooding comes back roughly every 30 years. Our data goes back 23 years. So if that's true, we can't actually, we don't know about that. So I think kind of like paying attention to what people say, and like there are like in a lot of communities like older members who do have kind of recollections of events that are maybe less maybe they remember things that happened and the severity of that better. So yeah, but I do think it's kind of an unsolved problem to keep attention on after the emergency has passed. But I think it's like a good point to raise. So we're not like forgetting things once they stabilize. Any other comments? Marcia?
Yeah. What would you say? Like, I can think of many communication challenges with the people's trust in AI, and also maybe how it's important that it doesn't sound like this will happen, but this might happen, and how to be prepared. But what would you say are like the 3 biggest communication challenges?
Yeah, I think there's a lack of trust in general because of the lack of explainability. And I think like my more maybe controversial take as someone who builds the models is I think that's actually really warranted because I think like, not being able to explain it in the way we do a physical model is actually, a bit of a challenge. And even if we can extract explanations using kind of like machine learning techniques, it's still like we do have to kind of interpret what those mean. And it's not really like the same as we're writing a physical equation that's modeling flow, where we can say this is exactly how it's working. So in my mind, that's kind of like warranted as a lack of distrust, and it's the responsibility of the model to kind of help provide enough explanations and enough, or at the very least, like a sufficient accuracy that those kind of concerns can be dealt with. Just I guess as a last comment as we kind of wrap up. I think the on the other hand of that is people being too untrustworthy of it, even if the model is kind of beating physical models and beating like hot takes by researchers, because that's often how a lot of forecasting is also done for like areas that don't have a great model, where the researchers just kind of looking at data and being like, okay, based on my experience, I think that will happen. So I think it's a very important to communicate, and like if you want to do it in one sentence, the goal is not to be perfect with these models, because no model is. The goal is to beat the baseline. So I think if you're better than the baseline, then I think that's the model that should be used. So I think also like in the models that I was showing there are some that like it's not fully accurate, but it beats all the baselines. So that's like the best model we have. So we go with what's best available, and we try and fill in the gaps as best as possible. So yeah, so thank you everyone for attending, and thank you for your participation at this strange hour. Yeah. Thank you very much, and have a great morning, I think.
Thank you very much. And I provided the link to the survey if you can take some minutes to.
Yes. There's also a QR code that they told me to put in here.
Thank you so much. Thank you, Jessica. Excellent dissertation.
Thank you very much. Have a great day.
Thank you.